Hey everybody, this is Larry. This is me going for Q4 of the weekly contest 249. Merge BSTs to create a single BST. So hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this problem. It was pretty tricky. But I think the hardest part about this one, and this is where I spent a lot of time on. If you watch me sub it live after the contest, you can see it. And also, join me on Discord because we go over the problems right after the contest. So if you want to nerd it up, if you want to hang out and discuss contest problems right after contests, come check us out. Anyway, so this one, the hard part, the most time that I spend on is actually to prove and doing proofs and stuff like that. So binary search tree, depending on who you ask, has some definition, but the key thing here is noting that it is strictly less than and strictly greater than. That means that if a number appears multiple times, it's always going to be false, because then no matter how you merge it, it's never going to be strictly less than or greater than. That cost me a WA actually. But with that in mind, it actually becomes just greedy. It's about, okay, so if there are multiple ways to connect something, then like I said, if a node appears multiple times, then this is already going to be false. So yeah, it's already going to be false because there's no way to squeeze into one tree where the two numbers and not all the numbers are unique, because by definition, all the numbers are not going to be strictly less than or greater than the other, right? So that's the key observation. Once you realize that, then it becomes easier, because then there's only one way to create a binary search, there's only one way to kind of connect the pieces together, and then you just have to check that it is a binary search tree afterwards. So the longest part that I have trouble was just to prove to myself that that is the case, because there's a lot of kind of maybe it's greedy, maybe you could call it greedy, maybe it's a forcing function, because if it doesn't get forced, then it just becomes false. If you don't force it, it becomes untrue no matter what, kind of thing. So that's the hardest part. I end up spending a lot of time, and I missed some edge cases because I was sloppy. But we'll go over my code real quick. But basically, what that is, how you solve it. The proof I'm not going to do because it's a little bit tough. Like I said, though, if there are multiple ways, then it cannot be a binary search tree, just because then neither of these can be true. Now that I think about it, I think that's a good enough proof. And then if there's only one way to construct a tree, you can construct a tree and then see if it's a binary search tree, because you can construct it, and then, like for example, in example 2, it is not a binary search tree. So that's basically there. Everything else I do is this is 100 lines of code, and if you know me, I usually don't do it this way. But I said what I said. I actually added a lot of additional checking, which are technically equivalent, to be frank. So yeah, so that's basically the things that I'm doing here. So I have a helper function that's count node. It is what it sounds like. I basically use it to count the number of nodes in all the roots. So then later I just double check that the count is good before we return the root. Otherwise, and this is a lot of code, otherwise I just have a lookup table of a value connecting a value with the node, and know that because this is unique, every root value is unique. We don't have to do additional checking here. I just add more counting. It's fine. And then this is the meat of my problem, which is that I also count the number of merges, because the number of merges should be n-1. That's why I have it here, because you have to, for n trees to get to one tree, the n-1 count. So that's what I did. And this is my goal getting function. I just make sure that I don't do duplicates. My code is very yucky, to be honest. It's very messy, but I'm just showing you what I did during the contest. You could watch me solve it live and how it evolved there, but I'm just going to go for it very quick. And basically, for every root that we haven't done it yet, I do a recursive like almost tape together the leaves for every leaf. I tape together more roots from the yeah, we look it up and we get the roots. So that's basically what I do here. Yeah, and there are other ways to implement this, but you know, mathematically, I guess the equivalent. And this is my tape, my merge, my tape function. Basically, if I already use this root, I return. Excuse me. Otherwise, I get the current node. I add it to a use set so that we don't reuse it later. If left is not none, then we try to tape the left, being that if this exists as a root, then I merge this, and this is basically the merging. I do recursion, and then later, and this is for cycles. That means that if we already removed it somehow, that means there's a cycle. So that means I set the count to some big number so that later it will be false. It's a very awkward way of doing it for sure, but that's basically the idea, is that I do recursive merging or taping until we can't, and then yeah, if we did not merge n-1 times, I return none. If we do not have only one node left at the very end, I return none. Otherwise, the root is the because we always delete, every time we merge something, we delete it from the roots. So at the very end, it should only have one node left. And if yeah, we should only have one node left. So I get as the root, and then I do a check. And this check is very straightforward, so I'm not going to go into it that deeply. It's a lot of weirdness. But basically, this just checks whether it is a binary search tree. Check node is BST. That's basically the idea. And it's recursive. It actually returns returns the min of this node and the max of this node of all the subtree. And you can go through the cases. And I think this is actually even... I think this is a binary, this is a LeetCode problem by itself, so I know how to do it. But if you have issues with this particular piece, you know, look for some binary search tree problems on LeetCode. So I'm not going to go over this part, but it just checked whether node is a binary search tree. And then basically at the very end, I do a check. I go if good, because I just set good to false if the invariants don't hold, and if it's good, and if the nodes we have on this root checks out, then this is a good root node. Otherwise, we return none again. So yeah, so we look at each node O of 1 time, because we do a couple of recursion, but everything is O of 1. So we look at each node O of 1, or for each node we have to do O of 1 work. So this is O of n time and space in terms of the number of nodes in the tree in general. So that's basically all I have. It's really not hard per se. I'm making it small so maybe you could see more of it. It's really not hard per se once you know what to do. The hard part is just kind of proving, at least for me, proving to myself that this is good enough, that greedy and forcing is good enough. So yeah. Let me know what you think. You could watch me solve it live during the contest next, but definitely let me know what you think. Let me know your questions, and I will, you know, watch me solve it live next. Okay. Different n binary search trees, but 3 nodes. No 2 roots are the same way. Okay, yeah, and I have to read this again. Such that trees of I is equal to, one of the leaves of I is equal to, okay. And we replace the leaf node in I with trees of J. We move tree, okay. Then you just combine trees maybe? This seems hard. I know what a binary is. So basically we can do this operation. We can replace with these 3 nodes. We can replace the 2 with the 2, 5 with the 4. Okay. Are these things unique? How does this work? Mm. 5 times 10 to the 4th. No 2 roots of the tree have the same value. That's a weird problem. Has any people solved it? Well, it's the same difficulty they say as Q3, but I don't know. Should have been faster. But no one did Q4 yet. That's a little bit weird. Okay. This is where the pen and paper might be helpful. I mean, this is trivially true. We put the 3 in the 2. Okay, so we have to combine all of them. Okay. So the roots, so each root, because the leaves can be in multiple places, right? Is that part of the hard part? It's a 3-noded binary search, so it could be a binary search tree that is like a linked list. But I wish they gave us one example where this is not unique, but I guess it's just something that I have to do. But I can't tell. Alright, let's look at the constraints again. No 2 roots, so only the roots are not the same. The value can be some high number. So in theory, you can have oh no, that's just, that would be not right. 2, 3, is that a valid input? Did I mess it up? Okay, I didn't mess it up. 1, 3. I don't know how to input this because they don't give an example of just a right node thing. Oh, I guess you just do, is this? Such a weird input. Oh, right. Whatever, just want to see if it works. So okay, so that is a valid input where basically you have if you have multiple places, then that's an interesting problem, right? I really don't know if I can solve this. If they're all binary search trees, so what is it about here that makes it not true? Oh no, this is true. What makes it here? So is there an answer that makes that right? I guess so. If there's another node that has a 5 and a 3, does that work? No. How can I make this right? 2, 5. Does it matter? Maybe not. Maybe if there's multiple ways, it doesn't really matter. Because if there are multiple ways, then you're probably not getting it anyway. Is that true? Can I come up with a case with multiple things where this is true? Oh wait, did I mess this up? No two roots have the same value, at most 3 nodes. One of the leaves. That's weird though. Is this a valid input? Let's see. 1, 2, 3. I wish they told me more, but I don't even know if this is a good input. Is this a valid tree? Okay, so I think they didn't really define this correctly. Still no one got it, so which is kind of scary. I think they really defined this really, because it cannot be a because for some reason it is not letting me choose something like, I don't know, everything to the left. Well, it'll be 3. Why not? And it's not an input, so which is not really in the thing. So then in that case, let me think about it again. So if it has multiple choice, what does that mean? That means that, well, okay. Strictly, okay, fine. Okay. Because if there's another one that is thing, it doesn't. 10. let's say 8, 10 here. The invariant here is such that basically this is good, but this is wrong. Now that's a case where you have to choose one. And you can choose the wrong one for sure. Because here you want seems like maybe it doesn't matter. I don't know. I'm gonna try it. But if still no one has gotten it, it's a little bit scary. Well, let's play around with some ideas. One person got it finally? Okay. Don't know if I know this one. But can it go both ways? Let's see. I guess not in that case. So basically we just, is there multiple answer? In this case, I don't know if I know the answer for this one. Okay, fine. Trees. In that case, okay, let's just put in a set. Lookup table, okay. Just you go to root dot value is equal to root, okay, and then now we just kind of okay. If let's go hold. Okay. You start at value, and then now we go to the left and the right. If that left is not known. Is equal to roots so put that right. What am I trying to do? Basically, what I want to do is set, if this is not none, then what am I doing? If this is good, then we go towards the left. Else we just don't care about it. Okay, fine. Okay, so it doesn't infinite loop. Good. Good, okay, fine, let's do it. How many people have gotten it so far? Okay, this. Okay, that makes sense. But then now it is whether this new tree is is binary search or it's a binary search tree. Well, okay. Once we do that, so it doesn't get used again. A couple of people have gotten it, so Alex, good job. Oh, okay, fine. After you do, I guess. What am I doing? Okay, but and then we didn't combine all the things. Otherwise, how do we get the root? Oh. Should have one node left, right? Okay. Oh, this should be none, I guess. Okay, so this. Just checking, I guess. This shouldn't be true, but. So root is equal to roots of keys. What okay, and now we just have to check whether it's a binary search tree. Is that right? A binary search tree if so that for each node we return the smallest number in the subtree and the biggest number in the subtree. Okay, so if node is none, okay, if node is a leaf, okay. Node should never be none. Okay. So the biggest element. Okay, let's just do it this way. Left. Big. Right min. Track right. If no dot value. Right min. If not this, then good is equal to false. Return. So then here we want to return, I guess just to keep it consistent, you want to return the smallest number in this tree. So I guess just left min actually. Left min, right max. Well, I guess that's just in general true. Okay, but we have to check the empty case. If so that's if it's a leaf. What if it's not a leaf? If no dot left is none, then we return. Max, okay. If not, no dot value is less than right min. Go to secret of force. Yeah. No dot value is the new max. Okay. Maybe this is good. Oh, wait. If good, return root, else return none. Let's see. Oh, this is not, this is the key. So actually I want the node. Is this right? This is wrong for this one because it is wrong. Okay, okay. I mean, I'm closer. What is the root? The root difference is 5, 3, 8, 2. So actually, I don't know what. I think this is right. Okay, so I do it correctly. And then what does that mean? That means that I suck in whatever, but oh. I think that's what I forgot. Okay, so that's good. Not confident about this, but let's give it a submit. Huh. That's a very quick wrong answer. So output is, oh, I have a wrong output. Why would that even happen? How does that? 1, 2, so let's see. This is 1, 3, 3, 1, 4, 2. That was the cycle that I was worried about. Okay, so then that's a silly thing. How do I count the number of nodes in this? Okay, let's see real quick. Yeah, I found a cycle. So it found a cycle immediate. Really? Oh, because it goes recurses twice. Basically, first sets up to 1. Goes right, and it sets up to 3. 3 goes left. No, but that doesn't make sense. Why? Do I not check for roots? You are right, I did not check. Well, I do this thing, but I should check it first. Dot left, dot low, not in used. Well, that doesn't change anything, does it? What am I doing here? What is used? 3 is used, but 1 is not used. So you should be able to do this, but I'm going about it incorrectly. I have to count the number of nodes. Does that make sense? Yeah, okay, fine. Okay, and then here we also subtract 1, right? Because we don't want to count the root, because that is, all of these will be on, okay. And then now, if good, and count nodes of root is equal to node count plus 1. Okay, so this is correct again. Let's give it a go. So now what did I have here? 3, 1, 1, 2, and then 2, 1. Did I check things incorrectly? I only delete if it's possible. Where am I? Also, I print stuff, so that's actually pretty bad. Whoops. But then I submitted it. But okay. Line 37. So what is the process here? So I go 3, I go 1, and then accuracy go 1, 2, 1. I mean, yeah, I guess I can check. From 0 to a million. This is such a hack. Okay. Am I gonna have 20 wrong answers? Okay. So just a lot of special cases. Yeah, thanks for the support. Hit the like button, hit the subscribe button. Join me on Discord. Let me know what you think about this problem in general, my explanations, whatever you need to ask. I'll probably put it in the comments or, you know, in a future video what to go over. Yeah, stay good, stay healthy, stay cool. To good mental health, and I will see you later. Bye bye.